Assalamu alaikum, guys. In this explanation lecture, we'll go through the O-Level Physics 5054 Paper 4 Alternative Practical of the Fastpapers Mock Championship 2026. Okay, so in the very first question, they ask us to find the external diameter of a test tube using two wooden blocks. Okay, so what we do is place the two wooden blocks beside the test tube. We lay the test tube flat on the bench and place two wooden blocks on two sides of the test tube. And then we measure the diameter or the distance between the two wooden blocks using a vernier caliper. These two diagrams show the setup, and we simply measure the distance between these two using a vernier caliper. Okay. The student clamps the test tube in a stand, fills a measuring cylinder to the 100 cm cube mark with water, pours some water from the measuring cylinder into the test tube. The arrangement of apparatus is shown in figure 1.1. The test tube containing water is also shown full size in figure 1.1, figure 1.1 over here. Measure the height h of the water in the full size test tube in figure 1.1. Okay, so they ask us to find this height. Record each in centimeters to the nearest millimeter in the second row in table 1.1. Okay, so if we measure the value of h using our regular ruler, we get a value of 3.2 centimeters right over here. Figure 1.2 shows the volume VR of water remaining in the measuring cylinder. Record VR in table 1.1. Okay, so the value over here is 89 centimeters cube, 89 cm cube. Record the volume V of water in the test tube. Record your answer in table 1.1. Okay, so the volume V of water in the test tube. Water inside the test tube was poured from the measuring cylinder. The measuring cylinder initially had water up to 100 centimeter cube mark, and now it has water up to the 89 centimeter cube mark. So the amount of water poured into the test tube would be 100 minus 89, which is 11 centimeters cube. The student adds more water from the measuring cylinder into the test tube, measures and records the new values of h and v are in table 1.1. Repeats the procedure for three more values of h and vr. The student's results are shown here in this table. On the grid, provided plot a graph of v on the y-axis and h on the x-axis. Start both axes from the origin and draw the line of best fit. Okay. Now, we have v on the y-axis and h on the x-axis. The values of h, well, our graph starts from 0, and the maximum value of h is 14.2. We have 1, 2, 3, 4, 5, 6, 7, 7.5 boxes. Since our maximum value of h is 14.2, we can simply take each of these boxes as 2 centimeters cube. So from 2, 4, 6, 8, 10, 12, 14. Now this value right here is going to be 15. So the first value of h, which is 3.2, will start somewhere around here in this region, and it will end somewhere around here. Okay, so the v-axis, the y-axis starts from 0 again, and it should end somewhere which is above 53. We have 1, 2, 3, 4, 5, 5.5 boxes here. The maximum value is 53, so we can take the value of each box as 10. 10, 20, 30, 40, and 50. This right here would be 55. Okay, so the first value is 3.2 and 11. This right here is 3, so 3.2 would be over here. 3.2. And the value of v is 11, which would be right here, 11. So the coordinate would be exactly here. That's our first coordinate. In this manner, if we plot all the values of v and of h, we get a graph that looks like this. Now, we need to compute or calculate the gradient of this line. So to calculate the gradient, we select 2 points from the line itself. Okay, so one point should be selected from the top portion of the graph, and another point should be selected from the bottom of the graph, so that the distance between the 2 points selected for the gradient is as high as possible. Okay, so let's select one from the top. This right here seems like a good coordinate. Uh, the value here is 12 on the x-axis and 45 on the y-axis. Okay, since we've circled our plots, it's best to use a different sign, let's say across, to indicate our points selected for the gradient. The point here is 12 and 45. Okay. Another point from the bottom of the graph, we can take this value right here, this coordinate. The coordinate here is 4 on the x-axis and 15 on the y-axis. So the two selected coordinates are 12, 45 and 4, 15. 12, 45 and 4 and 15. The gradient would be a difference in the values of the y-axis, 45 minus 15, over the difference in the x-axis. So 12 minus 4, which is approximately 3.75. 3.75. Now, if the test tube is a perfect cylinder, then the internal diameter d is given by the equation shown here. Use your values of m to calculate the value of d. So d would be square root of 4 times the gradient, which is 3.75, over the value of pi. Computing this gives us a value which is approximately 2.19, 2.19 centimeters. Now, your value of d is approximate. State one difficulty in measuring the height h of the water in the test tube and suggest how this difficulty can be overcome. Okay, so it's difficult to judge the, okay, now this right here is an image, so it's pretty easy to tell where the water level starts and where it ends. But in a real situation, it's quite difficult to tell exactly which part of the test tube holds the top surface of the water. And the bottom of the test tube is rounded, so it's difficult to tell where we should end our measurement of h. So it's difficult to judge where the value of h starts and where it ends. In order to overcome this difficulty, what we can do is take a meter rule and clamp it very close to the test tube. Okay. Suggest another reason why your calculated value for d is only an approximate. Now the question here tells us to assume the test tube is a perfect cylinder, but the test tube is not a perfect cylinder. It's not uniform. First of all, it's rounded at the bottom, plus the walls of the test tube are not completely straight, they're not uniform. So the assumption that this test tube is a perfect cylinder was not entirely correct. The test tube itself is not a uniform cylinder. Measure the external diameter d of the full-size test tube shown in figure 1.1. Now, if we use our rule to measure the value of d here, we get a value of 2.4 centimeters. Use your answers for E2 and G1 to calculate the thickness of the glass in the test tube. Okay. Now, we have two diameters. One of them is the outer diameter, and one of them is the inner diameter. Let's draw the inner diameter like this. Okay. Now, the outer diameter is capital D, inner diameter is smaller d. The thickness would be the outer thickness, the outer diameter minus the inner diameter, the difference between these two. Now, if we compute the difference between these two, we are getting the thickness on this portion of the test tube and also on the opposite portion, right? So what we do is divide this value over 2, which only leaves us with one of these values of length, and that value of length is the thickness of the glass. So computing this will give us 2.4 minus 2.19 divided by 2, which is approximately 0.11 centimeters. 0.11. Okay, on to the next question. A student is investigating the refraction of light by a transparent block. She uses her results to determine a quantity known as the refractive index of the material of the block. The student's read race sheet is shown full size in figure 2.1. The student places a transparent block ABCD, the transparent block ABCD over here. at the center of the ray trace sheet as indicated in figure 2.1. She draws around the block, she removes the block and then draws lines NL and EL. Lines NL right over here and line EL right over here. Measure the angle theta between the lines NL and EL. Now, if we measure this angle using our protractor, we get 30 degrees. It will decrease over here. The student places two pins P1 and P2 on the line EL a suitable distance apart for accurate ray tracing. Suggest the suitable distance between the two pins. Okay, so ideally the distance between the two pins should be greater than or equal to 5 centimeters, but at the same time it can be too high. So generally the acceptable range is from 5 centimeters to about 15 centimeters. So in this case, we're going to keep the length as 5 centimeters. 5 centimeters is like the safest bet. The student replaces the block. She views the images of P1 and P2 through the block from the direction indicated by the eye in position X right here. She places two pins P3 and P4 so that pins P3 and P4 and the images of P1 P2 all appear exactly one behind the other. P3 and P4. She labels the positions of P3 and P4, then removes the block and pins from the retrace sheet. She draws a line FG through pins P3 and P4, extending it as far as CD. Extended it as far as CD, okay. Draw normal to CD at point G and extend it to meet AB. Okay, so this line right here is the normal at G, which is extended all the way to AB. Label the point at which this normal meets AB with the letter H. So this point right here would be the letter H. Draw a line joining points L and G. Extend line EL until it meets GH. Okay. Draw a line joining L and G. L right here and G right here. So we draw a line that joins the points L and G. Extend EL until it meets GH. EL is this line, so we simply draw a straight line until the normal right here. Measure the length A of line LG. Line L to G. If we place our rule on L and G, we get a value of 6.4 centimeters. Then measure the length B of line LK. Line LK would be this right here. Oh, but K is the point of intersection between the line extended from EL connected with GH. So this right here is K. And the length of the line LK would be 4.3 centimeters. Now if we compute A over B, 6.4 divided by 4.3, we get a value which is approximately 1.49. The student places a mirror against side CD with the reflecting surface facing towards the block. She views the images of P1 and P2 from the direction indicated by the eye in position Y in figure 3.1. Okay, so the student places a mirror over here, which is facing towards that direction. So the line that hits the mirror from here will reflect back in this direction. Okay, and the image is seen by the eye in position Y. Extend line RS until it meets GH. RS until it meets GH. So RS is given already. We extend it until it goes all the way to GH. Then we label the position, the point of intersection with the letter H. With the letter T right over here. Measure the angle alpha, where alpha is a smaller angle between the lines RT and GH. Okay, so RT and the angle between RT and GH would be this angle right here. Let's call it theta or alpha as they've mentioned. Measuring this angle using our protractor gives us 27 degrees. 27 degrees. A student suggests that that angle alpha and angle theta measured in part A should be equal. State whether the results support this suggestion. Justify your answer with reference to the results. Okay, now 27 degrees and 30 degrees are within 20% of each other. So we can say that the two angles are indeed equal because they fall within the experimental accuracy of 20%. Suggests why different students all carrying out this experiment carefully may not obtain identical results. Now, when we align these pins, the pins were not, of course, they were not initially there. The pins were placed after looking at the images of P1 and P2, right? So aligning these pins is quite difficult and it varies from person to person. Even if the same person does this experiment again, the values will not be exactly the same as before. Right. So on to question number 3. A student has 50 small glass beads of different sizes and shapes in a jar as shown in figure 3.1. One of the glass beads is spherical, suggest a piece of apparatus that measures the diameter of this bead more accurately than a ruler. Okay, so more accurate than a ruler would be a vernier caliper or a micrometer screw gauge. Both are valid instruments. This bead is drawn to full size in figure 3.2 right over here. Use a ruler to measure the diameter of the glass bead in figure 3.2. So if we place our 30 centimeter or 15 centimeter rule, we get the diameter from here to here as 3.4 centimeters. Explain how you measured the diameter as accurately as possible. You may draw on the diagram if you wish. Okay, so what we can do is make use of two set squares and draw two parallel lines on two ends, opposing ends of this circle. Now, if the two lines are parallel, the difference in length between these two lines would give us an accurate value of the diameter. The student finds the average density of the glass beads in the jar in figure 3.1. Describe a method to find the total volume of the glass beads. 50 glass beads. State the apparatus used to explain how it is used. You may draw a diagram if you wish. Now, you may draw a diagram if you wish, so if you don't draw a diagram, that is also fine. So what we do is we take a measuring cylinder and fill it with water. Let's say this is water, and then measure the volume over here. Let's call this what do we say? VW, volume of water. And then inside the same volume of water, we add all our glass beads. And then we measure this volume again. Let's call that VB, the volume of the glass beads. Actually, let's call it the WB, water and the beads. So the volume of the beads would be the total volume of water and the beads minus the volume of water only. So what we do is fill the measuring cylinder with water, then put all our glass beads inside the measuring cylinder, which already had water. We ensure that all of the glass beads are completely submerged in water, and then measure the volume of water and the glass beads again. If we subtract these two values, we get the volume of the glass beads only. State a precaution taken to ensure an accurate value for the volume. First of all, we need to ensure that the measuring cylinder is large enough to hold both the water and the glass beads. We also need to ensure all of the glass beads are completely submerged in water after adding the glass beads. The total volume of the beads is 196 centimeter cube and the total mass is 523. Find the density using this equation. Okay, now if we uh, divide the mass over the volume, 523 grams over the volume, which is 196, we get 2.67 grams per centimeter cube because the mass is given in grams and the volume is given in centimeters cube. A student places a small metal container inside a larger metal container. As shown in figure 4.1, there is an air gap between the two containers, air gap right over here. The student investigates the effect of the size of the air gap on the rate of cooling of hot water. Plan an experiment to investigate the effect of the size of the air gap between the small metal container and larger metal container on the rate of cooling of hot water. The following apparatus is available. The apparatus shown right here. You can also use other apparatus and materials that are usually available in a school laboratory. You are not required to do this investigation, of course not. In your plan, you should explain briefly how to carry out the investigation. State the key variables to control. Draw a table or tables with column headings to show how to display your readings. We don't really need to input any readings because we don't have any readings. Explain how to use your readings to reach a conclusion. A diagram is not required, but yeah, we may draw one if it helps our explanation. Right. Now, the rate of cooling depends on the total volume of water. It depends on the surface area of the water. It also depends on the initial temperature of the water. So these are variables that we need to control, that we need to keep constant. The initial temperature, The volume of water, let's call that V, and the surface area of the water, let's call that surface area. Okay, so if these three are kept constant, the rate of cooling will only depend on the size of the air gap. Okay, so we have a small metal container. What we do is we pour boiling hot water inside this small metal container with a thermometer inside. So a thermometer would be inside. Now, boiling hot water is, of course, very close to 100 degrees Celsius. We wait for that temperature to drop down to, let's say, about 90 or 95 degrees Celsius, and we start our stopwatch when our temperature reaches that specific initial temperature that we've selected. So let's say the initial temperature is 90 degrees. We start our stopwatch when the temperature reaches 90 degrees from 100 degrees, and we measure the time taken for the temperature to drop from 90 to, uh, let's say, 85 or maybe 80 degrees Celsius. Now, this gives us the time taken for the initial temperature to drop from 90 to 80. Now, this rate of cooling, the time taken, will depend on the size of the air gap. The longer time it takes, the lower the rate of cooling. So if it takes longer, rate of cooling will be lower. If it takes less time, the rate of cooling will be higher. This way, we change the size of the air gap by taking different larger metal containers, and we can tabulate the data in a table that looks like this. Now, the size of the air gap can be measured by finding the diameter of the larger metal container. Let's call that diameter D, capital diameter, the larger diameter, and the diameter of the smaller metal container. Let's call it smaller d. Now, very similar to our first question, which was right here, we can find the thickness of the glass or in this question by dividing the difference in diameters by 2. So similar to our first question, we can find the air gap, the size of the air gap, by computing the diameter of the larger metal container minus the diameter of the smaller metal container and dividing it by 2. This gives us the size of approximately the size of the air gap. Now, under column 2, we have the time taken. This time taken is the time for the temperature to drop from 90 degrees Celsius to 80 degrees Celsius. The initial temperature is kept constant. The volume and the surface area will also be kept constant. Now, if we have multiple values of air gap size and time taken, our conclusion would be, the conclusion that we can reach would be, the longer it takes, the slower the rate of cooling. So what we can say is the air gap size that shows the highest value of time has the lowest rate of cooling. All right, so here is one way of answering the question. This is basically the written form of what I just explained. So that concludes our paper for today. I hope you guys do well in your exams, inshallah.